Now let's look into vibration of single degree of freedom systems under periodic forces. We have already learned the vibration under harmonic forces. Harmonic force is a special type of periodic force. So now we will look into the vibrations under any periodic force. So in this case, the single degree of freedom system is acted upon by a force which is a periodic function in time. So what is a periodic function? We can say a periodic function has a specific portion of it within a specific duration repeating itself indefinitely. So we'll understand this using an example. So this is an example of a periodic function. This function is called sawtooth function and this has a period t0. So after the duration of t0, the function repeats itself. So this much specific portion of this function gets repeated indefinitely. So let's see one more example. So this is also a periodic function and this period is t0 and this portion of this function gets repeated indefinitely. So a function pt is said to be periodic with a time period of t0 if pt, the value of the function at t, is equal to pt plus j t0. That is, pt is equal to the value of the function after multiples of t0. So pt is equal to pt plus j t0, where j ranges from minus infinity to plus infinity. So this function continues indefinitely. So now let's see how a periodic function can be represented in terms of harmonic components. So we can do that using Fourier representation. So any periodic function pt can be represented like this using Fourier representation. So here a0, aj and bj are constants and we have cosine and sine functions as well. So this periodic function can be split into multiple harmonic functions, that is, functions of cos and sines. The series has infinite number of terms and as the value of j increases from 1 to infinity, that particular harmonic will have frequency equal to j times omega naught. Both these harmonics will have same frequency equal to j omega naught. And the fundamental harmonic in this excitation has the frequency omega naught. That is when j is equal to 1. So omega naught is equal to 2 pi by t naught, where t naught is the period of the periodic force. And the coefficients of this Fourier series, that is a0, aj and bj, can be expressed in terms of the periodic function itself, that is pt. a0, the first coefficient, is expressed as this. It is 1 by t0 integral 0 to t0 pt dt. So that means this is the average value of the periodic function. So if you do this, we'll get the average value of this function pt. So that is equivalent to the first coefficient. And aj, that is the coefficient of the cosine terms, are calculated like this. 2 by t0 integral 0 to t0 pt cos j omega naught t dt. So to find aj, we have to integrate pt multiplied by the cos harmonic. And it can be found out for all the values of j ranging from 1 to infinity. Similarly, the coefficient of the sine terms can be calculated as 2 by t0 integral 0 to t0 pt multiplied by sine j omega naught t dt. This also can be found out for all the values of j. So if you can calculate a0, aj and bj, we can split the function pt in terms of harmonic components. We have seen that the coefficient a0 indicates the average value of pt, and the coefficients aj and bj indicate the amplitudes of the jth harmonics, and the jth harmonic will have frequency equal to j times omega naught, and omega naught is the frequency of the fundamental harmonic, that is equal to 2 pi by t naught. Theoretically, this series has infinite number of terms. That means we need infinite terms to represent this periodic function in terms of harmonics. But in reality, only a few terms are sufficient for this Fourier series. So with very few terms, this series will converge to the periodic function. If this function has any discontinuity, at the discontinuity, this Fourier series will converge to an average value, that is the average of the values to the left and to the right of the discontinuity, that is average of the neighboring values of the discontinuity. Now let's find the response of damped systems to periodic force. We have already learned the response of damped systems under harmonic forces, and we learned that transient responses due to initial displacement and velocity decays in time. So most of the analysis are focused on steady state of the system. So after some time, the transient responses will die out and only the steady state response will be prevalent. And the steady state response will be present as long as the force exists. So we can focus on the steady state response of this system. Now, the response of a linear system to a periodic force can be determined just like that of a harmonic system. And here we combine the responses to individual excitation terms in Fourier series. So we just have seen that a periodic function can be separated into different harmonics using Fourier series. So the response of a periodic force can also be treated as a sum of the responses of the individual harmonic forces. So the response to a periodic force is equal to sum of the responses to many harmonic forces. So when a constant force is applied to a single degree of freedom system, the steady state response is given by A0 by K. So this is like a static response. The force is constant and we are looking at the steady state response. So this is equal to the static response of the system, that is A0 by K. Now let's see what is the response of damped systems to sine force. This is exactly what we have seen during harmonic vibrations. This is the equation of motion of a single degree of freedom system acted upon by a sine force. The force is P0 sine omega t. So we have derived the response of this system. So we can rewrite this equation like this, where damping ratio is defined as C by CCR and the critical damping coefficient is 2m omega n. And the steady state response of this system is of the form C sine omega t plus D cos omega t, where this omega is equivalent to the forcing frequency. So, and we had derived this coefficients C and D, and the coefficients are given by this. So, if you can calculate this coefficients, we can find the steady state response of this system under sine force as this. So now let's look at the response of a damped system under cosine force. If we do a similar derivation as in the case of sine force, we can find the response due to a cosine force. So we can find the steady state response due to a cosine force is equal to C prime sin omega t d prime cos omega t. And C prime and d prime can be calculated in the similar way we did for sine force. So if you do the derivation, we would get the values of C prime and d prime as these. And this C prime is equal to minus d. D is the coefficient of the cos omega t term in the steady state response when the acting force is a sine force. And we can also calculate d prime as this, and that is equal to c. So now we can come back to the Fourier representation of the periodic force, and let's find the response of damped systems to periodic force. So in the Fourier series, we have this cos terms. So the response due to this harmonics, the cosine harmonics, can be calculated using the expression we just saw previously. So the steady state response due to the cosine force Pt is equal to Aj cos j omega naught t, that is the jth cosine harmonic. So the response due to this can be found out as Aj by k. So that term is equivalent to P naught by k, as Aj is the amplitude of this force. So it is Aj by k, then 2 zeta beta j, and beta j is frequency ratio of this harmonic. So for that particular harmonic, the forcing frequency is j omega naught, and omega n is the natural frequency. So this is equivalent to our omega by omega n term, that is the frequency ratio. So this beta j is equivalent to the frequency ratio for this particular harmonic. So we have Aj by k 2 zeta beta j sin j omega naught t plus 1 minus this frequency ratio square cos j omega naught t, the whole divided by 1 minus frequency ratio square plus 2 zeta frequency ratio, the whole square. And we can also write the similar expression for the sine terms in the Fourier series. So the sine harmonics is Bj sine j omega naught t. So the response due to this sine term would be this. So that would be Bj by k, again that is equivalent to the P naught by k term, and 1 minus frequency ratio square multiplied by sine j omega naught t minus 2 zeta Bj cos j omega naught t divided by the same numerator. So if you just compare these two responses, that is the responses to sine and cos forces, the expression is quite similar. The numerator is same, and this constant term is amplitude by k. So that is Aj by k here and Bj by k here. Both the numerators have sine and cosine terms. The coefficient of cosine term in this expression is equal to the coefficient of the sine term in this expression, and the coefficient of sine term in this expression is 2 zeta beta j, and the coefficient of the cos term here is minus 2 zeta beta j. So they are like negative of this is the coefficient here. So now we have the response due to cosine force and sine force. So now we can add all these responses and find the response due to the periodic force. These expressions become indeterminate if theta is equal to 0 and this in beta j becomes 1. If any of the beta j's becomes equal to 1 and theta is equal to 0, both these expressions will become indeterminate. So what does that mean? It means that in that condition, the steady state is unbounded. So we have seen unbounded steady state in the case of undamped resonance condition. So that means the steady state response was increasing without any bound. And these unbounded steady states are not meaningful. They are not realistic because in such cases transient response never decays. That is because theta is equal to 0. All real systems will have some amount of damping. So the steady state response for any real system will not be unbounded. So in our analysis, we'll consider only situations where theta is not equal to 0 and beta j not equal to 1. So if this condition is satisfied, then we will never get an unbounded solution from this expression. So the steady state response of the damped system due to a periodic excitation is equal to the combination of responses to the individual terms in the Fourier series. So the total response is equal to the sum of the responses to the individual terms in the Fourier series. So this is due to the constant in the Fourier series, and this is the response to the cosine functions, and this is the response to the sine functions. The sum of all will give the total response due to this periodic excitation Pt. So if we substitute the equations of the coefficients in the previous expression, we would get the response of the SDOF system due to a periodic force, and the expression is this. Here A naught by K is equivalent to a static response, and then we have harmonic responses, that is sine and cosine functions. The amplitude of this harmonic is given by these big expressions. You can calculate it if we know the value of the damping and the frequency ratio. And the frequency of a harmonic is equal to j times omega naught, where omega naught is 2 pi by t naught. This response will be again a periodic function and its period is t naught. The total response is a sum of multiple harmonics, and the relative contribution of various harmonic terms will depend upon two major factors. One is the amplitudes Aj and Bj. So if the amplitudes Aj and Bj are high, the jth harmonic will contribute more to the response. And if the frequency ratio of the jth harmonic, that is beta j, is near 1, then that harmonic component will also dominate in the response. So when the frequency ratio is close to 1, the amplitude tends to be very high. So that harmonic will majorly contribute to the total response. Now let's solve an example problem in periodic vibrations. A single degree of freedom system with natural period Tn and damping ratio theta is subjected to the periodic force shown below. So this force has amplitude P0 and period T0. Expand the forcing function in its Fourier series. Determine the steady state response of an undamped system. For what values of T0 is the solution indeterminate? So from this forcing function, we can understand that this forcing function is an even function. That means this function is symmetric about the y-axis. That is, p at time t is equal to p at the time minus t. So if this condition is satisfied, this function is an even function. Now we can represent this function as a equation. So this is a straight line. So we can find the equation of the straight line. So that would be p naught multiplied by 1 minus 2 by t naught t. And this is valid when t is between 0 and t naught by 2. The same equation will be valid when t is minus. That is when t is between 0 and minus t naught by 2. And if this function is defined for a duration of t naught, that is the period of this function, then it is defined everywhere, because then it's a repetition of the same portion everywhere. So this is how we can write this forcing function as an equation. So to find its Fourier series, the first step is to find the coefficient a naught. So a naught is defined as 1 by t naught integral minus t naught by 2 to plus t naught by 2 pt dt. So we can substitute the value of pt here and can carry out this integral, and we would get p naught by 2. So a naught, or the constant term in the Fourier series, is p naught by 2. Now we will find aj. So aj can be found out as 2 by t naught integral minus t naught by 2 to t naught by 2 pt times cos j omega naught t dt. So this aj is the amplitude of the jth harmonic, the cosine function, and the frequency at the jth harmonic will be j omega naught. So if you carry out this integral, we would get the value of aj as 2 p naught by pi square j square cos pi j minus 1. So cos pi j will have two different values depending upon the value of j. So the value of j is integer. So for odd integer, the value within the bracket would be 2. So aj would be 4 p naught by pi square j square. So when the value of j is even, that is when j is equal to 2, 4, 6, etc., this becomes 0. So aj will be 0. Now we need to find out the term bj. So bj is given by 2 by t naught integral pt sine j omega naught t dt. So we have already seen that pt is an even function, and sine, we know that it's a odd function. So that means sine minus x is equal to minus sine x. So if we integrate an odd function from minus t naught by 2 to t naught by 2, that is over a period, that becomes 0. So this term bj is equal to 0 for all values of j. So the forcing function pt can be represented as a Fourier series like this: p naught by 2 plus 4 p naught by pi square summation of odd values of j 1 by j square cos j omega naught t. So this is how we can represent the forcing function in terms of harmonic functions. So now we can find the response, the steady state response of an undamped system due to this periodic force Pt. We know the coefficients and we can write the expression of ut by substituting these coefficients in the expression we have derived earlier. So this is our expression for the steady state response, and this has infinite number of terms. So theoretically this response is the sum of infinite number of terms, but if we plot this expression we can see that only a few terms are necessary to calculate this response. So if we consider only the first two terms, that is this term and the first of this term, we would get this blue curve. So this is plotted for some values of p0 by k and omega by omega n. If we consider three terms, we would get this green curve, and if we consider four terms, we would get this black curve. As it is evident from this picture, the sum of three terms and sum of four terms are very identical. So that means the three terms or four terms of the series converges to the actual steady state response. So we need not consider infinite number of terms to get this accurate response. We can get the correct response with a very few terms itself.